Hello students and welcome to our physics revision class. So today's discussion will be about rotational motion or angular motion, which is a 6th unit in grade 11 physics. So in this unit we are going to consider a rigid body, a rotating rigid body about an axis. So whenever a rigid body is rotating about a fixed axis, then the particles of the rigid body rotates with a circular motion. So the motion of the objects can be described using two quantities. There are some linear quantities describing their motion and there are some angular quantities, okay? So for example, if the ice particle is rotating from this point to this point, from position 1 to position 2, it will move such a displacement which we call angular displacement. I mean tangential displacement or linear displacement, that's the arc length. And when the object is moving from this to this position, it makes some angle theta with the center, so we call that angular displacement. So when the linear displacement is continuously changing with time, then we'll have linear velocity, and when the angular displacement is changing with time, we're going to have what we call the angular velocity, okay? So if we assume that the initial velocity V initial at this position is Vi or V naught, and if the velocity of the object changes at this position as V final, then the object has accelerated between the two positions. That kind of acceleration is called linear acceleration or tangential acceleration, which is given by rate of change of linear velocity. And linear velocity is given by rate of change of linear displacement. So similarly, since the angular displacement is continuously changing with time, we are going to have also an angular velocity, which is the rate of change of angular displacement. So if the object's angular velocity at position 1 is omega naught, and if its velocity changes to omega final at position 2, then there will be an angular acceleration, and the angular acceleration is defined as the rate of change of angular velocity. Okay? So these are the two kinds of quantities. There's a linear quantity and there's an angular quantity when an object is rotating about a fixed axis, okay? So there is a relationship between the angular and the linear variables. And we know that, for example, the linear variable, the displacement is measured in meter, but the angular, since an angle can be measured using 3 different units of measurement, it can be measured in revolution, it can be measured in degree, or it can also be measured in radian. So there is a mathematical relationship between the 3. We know that 1 revolution is equal to 2 pi rad, and which is equal to 360 degree. Okay? So we have a mathematical relationship between the linear and the angular variables. Linear displacement r times angular displacement, linear speed r times angular speed, and linear acceleration r times angular acceleration. So, if the rotating rigid body is rotating at a constant acceleration, then we're going to have a uniformly accelerated rotational motion. So, for a uniformly accelerated rotational motion, these equations will be applied for the linear motion, the translational motion, and these equations will be applied for the angular motion, okay? For the angular motion. For example, we can calculate the linear displacement s, or the arc length, as initial velocity plus final velocity times t divided by 2. Similarly, we can calculate the angle that the rotating rigid body or the particles of the rigid body makes with the center using these mathematical expressions. Okay? So another important concept in rotational motion is about moment of inertia. So moment of inertia is a quantity that describes how the mass of the objects are distributed with respect to a certain axis of rotation. So mathematically, the moment of inertia I is given by the summation of mi ri square, where I runs from 1 to n, okay? Number of particles. If there is a continuous distribution of mass, we can use integration to calculate the moment of inertia, okay? That's for grade 12. Okay. So the next concept is about rotational kinetic energy. So rotational kinetic energy is energy possessed by the rotating rigid body, and it can easily be calculated using E is equal to half times I times omega square, where I is the moment of inertia. Okay, this is the quantity that plays the roles of mass in angular motion, moment of inertia. All right, so what if the object is rolling without slipping? Okay, if it's rolling without slipping, then the kinetic energy will be of two types. Okay, the object will have a translational kinetic energy and a rotational kinetic energy. Okay, so the total kinetic energy will be half mv squared, that's the translational kinetic energy, plus half times I omega squared, that will be the rotational kinetic energy. Okay, now let's see how we can apply Newton's second law for angular motion. We know that Newton's second law for linear motion states that net force acting on an object is equal to mass times acceleration. So we know that force net is equal to, like torque is defined as force over torque is equal to force times R. So over R is equal to M times R times alpha. So torque is equal to mr squared times alpha. We know that mr squared represents the moment of inertia. So Newton's second law for rotational motion can be stated that the net torque acting on an object is equal to I times alpha, the moment of inertia multiplied by the angular acceleration. Similarly, we can also calculate the work done by the net torque. We know that from linear motion, work done is equal to force dotted with displacement, and we know that this is torque over R dotted with displacement is theta times R. R can be cancelled with R, so the net work done by net torque is equal to theta dotted with tau. That's the that's the torque. Okay. So another important term in rotational motion is angular momentum. So the angular momentum of a rotating rigid body is given by R times the linear momentum, or simply the angular momentum can be described in terms of I times omega. Okay, moment of inertia times the angular speed. So if we rearrange here Newton's second law, we come up with net torque acting on an object is equal to I times alpha. We know that I into alpha is equal to final speed, angular speed minus initial angular speed divided by change in time. So I times omega final means angular momentum final minus angular momentum initial divided by change in t. So net torque is equal to change in angular momentum over change in t. Or the net torque acting on an object is equal to the rate of change of angular momentum. So if the net torque acting on the rotating rigid body is 0, then the change in angular momentum of the object will be 0. That means angular momentum final will be exactly equal to the angular momentum initial. Angular momentum initial is I initial times omega initial is equal to I final times omega final. Okay, so this from this mathematical expression you can tell that whenever the value of I is increasing, the value of the angular speed is decreasing. Okay, the angular speed is decreasing. So this is all about rotational motion. I hope you find this very useful, and I hope you will do some practical examples on how to apply these mathematical expressions. Until next time, stay safe.